Assalamualaikum everyone. Today's episode is a revised excerpt of a past upload on direct current circuits. It focuses on the difference between an open and a closed direct current circuits. So stick around, watch and learn. The given question. The figure shows a source, which is a battery, with an EMF equal to 12 volts and an internal resistance equal to 2 ohms. Question: what are the voltmeter and the ammeter readings? The electromotive force, or the EMF of the battery, is given equal to 12 volts. The battery is a non-ideal source with an internal resistance denoted by small letter r equal to 2 ohms. And examining the circuit diagram shows that the wires to the left of point A and to the right of the ammeter are not connected to anything, making the circuit an open circuit. All right. So we are also assuming that the voltmeter, all right, has an infinite resistance, while the ammeter has practically zero resistance. All right. So in an open circuit like this, what do you think is the relationship between the battery's EMF and the voltage across points A and B? You'll find this out in just a short while. Since the ammeter is not completely connected to the battery, we conclude that there is no current that would pass through the ammeter. So the ammeter reads zero current. When current in the circuit is zero, we say that the potential difference across points AB or across the battery is simply equal to the battery's EMF. So the voltmeter reads 12 volts. Notice that the voltmeter is connected parallel to the battery. So conceptually, in a parallel connection, the voltage across each load is just the same. That means whatever is the potential, okay, across the battery is also the potential that is measured by the voltmeter. Okay, so the reading in the voltmeter is just equal to the EMF of the battery, which is 12 volts. What if the same battery is now connected to an external resistor, big R? Okay, so the external resistor, big R, has a resistance equal to 4 ohms. All right, so this new uh, setup or circuit diagram is an example of what we call, all right, a closed circuit. all right? Because there is now a continuous flow of the positive net charge, all right, from the positive terminal of the battery to the negative terminal of the battery, all right, as emphasized by the arrow which represents the current, all right, in the circuit. So in this figure, the current or the flow of the positive charge is in a counterclockwise manner. All right. So the same amount of current that is generated by the battery, okay, passes through the big resistor, all right, as well as through the ammeter and of course through the battery. That's why we say that the current in the circuit is the same at any given point in the circuit, whether it is at point A, all right, whether it's at point A prime, all right, at point B prime, or at point B, all right. And this current around the circuit is exactly the current that is measured by the ammeter, all right. The ammeter is so designed to have almost a zero resistance, all right. So whatever passes through the ammeter is exactly the same current, all right, that passes through any point in the circuit. The same current measured by the ammeter is the current that passes through the big R, all right, or through the battery, that is, all right. And this current can be calculated, all right, using the formula current I equals the EMF of the battery divided by the sum of the internal resistance small r and the big resistance capital R. Or when we substitute, we have for the EMF of the battery, which is 12 volts, divided by the value of the internal resistance of the battery, 2 ohms, and the big R, which is 4 ohms. So we get the current generated by the battery, or the current in the circuit, equal to 2 amperes. So in other words, this amount of current is what will be read by the ammeter. All right? The ammeter reading, therefore, is equal to 2 amperes. In the case of the voltmeter, which is designed to have a very high resistance, which implies that the current generated by the battery can in no way pass through the very high resistance voltmeter. All right? So no current can pass through the voltmeter because of its very high resistance. But since it is connected parallel to the battery, its measurement reading of the potential across the battery is actually equal to what we call the terminal voltage. All right? Terminal voltage, labeled B sub AB, is just the difference between the battery's EMF and the IR voltage, or the product of the current I and the internal resistance R. So if you get the difference, all right, that is 12 volts, which is the value of the battery's EMF, minus 2 amperes multiplied by 2 ohms, we will get the value for the terminal voltage B sub AB equal to 8 volts. So in short, the voltmeter reads 8 volts. We say that this terminal voltage of 8 volts is also the voltage across the big R, because you will notice that the voltmeter, the battery, and the external resistor big R are in fact connected parallel to one another, where conceptually we say, all right, that the voltage across each of them is just the same. Finally, we emphasize the following key concepts that were applied in this problem. First, the terminal voltage of a real, non-ideal source with an internal resistance equal to the EMF only if no net charge or current passes through the source. And the other one is to find the potential difference across a resistor, multiply the current through the resistor by its resistance. The potential difference across a source, such as a battery, differs from its EMF by an amount determined by the source internal resistance. And that concludes our tutorial. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.